Hello, everyone. This is Professor Ma, and this is the lectures on vectors. Uh, we use numbers to measure quantities. We use vectors to measure quantities and also the direction this quantity applies to. And so, such like what? Like when I punch, then there's a direction of the punch, and of course the force in the punch, and those there are two pieces of information we use. So or something like a point from here and move to a point over here and change from one position to another position. It can be represented by a vector, that is the direction it changed and how much it changed. So a lot of problems can be solved with these ideas of vectors. And how do we, in mathematics, we use the letters U, V, W to represent vectors. And sometimes we draw a little arrow on top of the indicator. We want to think of this as a little arrow. So that is thinking in terms of pictures, the geometries. Okay. And the quantity track, of course, the arrow gives the directions, and then the quantity is the length of the arrow that we draw. Okay, and that's also called the absolute value of the vectors. And we put absolute value around the vector means we want the length of the vectors. And we can do arithmetics with all these little arrows. Okay, and these arithmetics are based on geometries. And so here are the arithmetic vectors. What do we mean by two vectors are the same? Well, two vectors are the same if they point in the same directions and have the same length. It's just like if I were to write down 2 5s, you know, if I were to write the number 5 here and the number 5 here, and I say that the number's the same, yeah, and that they're the same quantity. $5 in my pockets versus $5 on the table, that the quantity 5 are the same. What can we do with scalars? We can stretch it and shrink it. So if I have a number lambda, which is called a scalar, in the vectors, then I can multiply the scalar to the lambda. And if the scalar is bigger than 1, like it's 2, then I stretch the vector twice as long. If scalar is half, that means I shrunk the vectors down to half the size. In particular, if the scalar is negative, we flip the directions of the vectors. The minus 2b will be pointing in the opposite directions from twice of b. Okay. And 0 times b is just a point, 0 vectors. How do we add? These are the most important things in doing the arithmetics of vectors. There's the parallelogram rules. So you have two vectors, and then the vector sum of these two vectors is we use the two vectors make a parallelogram, and vector sum is the diagonal. And we can the following views. Another way to look at this is quite useful. How do we make that diagonal? Is that we can take the base of one of the vectors and move to the tip of the other ones, and then form the diagonal. So I call it the base to tip additional rule. And this helps if I have more than two vectors. If I say I want to add these 3 vectors, that it's easier for me to use move the base to the tips of vectors, add, and then do that process again like this. Add the red and the green vectors first, and that I put the blue vectors and base to tip, and then the end result is the sum. It doesn't matter which one we move first, you always get the same sum. So the base to tip rules is very easy to see what the sum of a bunch of vectors are. And given two vectors, and if I know the angle between them, I can use the trigonometry to find out the diagonal length. So and we use we use cosine laws to accomplish that. Okay, vector subtractions. And how do we subtract vector? That's a tip-to-tip rule. And that is, if I want to find the difference of two vectors, I draw the tip of the vectors to the tip of the other vector. That's the difference, the subtractions between the two vectors. So the u minus v is from v to u. So this is the pictures for subtracting vectors. If I can put the vectors into coordinate systems with the base of the vectors at the 0, 0 positions, we call that vectors in the standard positions. And then in that case, I will use a tip to give the actual actual representations for the vectors. So the standard positions, this vector in the standard position is the 4, 2, and this is the vectors minus 2, 4 in the standard positions. They all based at 0. And 0 vector 0, 0. And in particular, if I know 2 points in space, like stay in the plane, and I want to know the standard position of these vectors, and the rules, the rule for finding the standard positions of from the point B, the base to the tips, is the tip minus the base. So in this case, the vector bt is going to be t minus b, and this is just arithmetics. And what you wind up is the vector minus pi part. And can do it in the vertical format. It's very easy. The arithmetics in this section is very easy. The ideas in here is that how to match up the arithmetic with the geometry, the directions of the vector, the sum of the vectors, the difference of vectors, and they all have pictures like these behind them. And so keeping track of the pictures, it's important. The length, the magnitude of the vector in standard position is very easy to calculate. That's just the length of the distance from the origins to the point AB. So it's given by the length formula. So here we calculate the standard positions, and then we calculate the length of the standard position formula, which is given by that. Scalar multiplications. How do we carry out scalar multiplication in standard positions? Very easy. We multiply the coordinate by the scalar. We do this by coordinate wise, we say. Okay. So if I stretch this twice as long, and then the new vector is going to be 4 minus 2. So we multiply the 2 to the coordinate. That will give me the new scaled vectors. How do we add? We add coordinate wise. They subtract coordinate wise. Okay, and this is basically it. And so, for example, here are two vectors. We want to find the algebraically what's phi times u minus 3 times v, and here's the pictures. And basically those are u and v over there. I use very small scale because I'm going to stretch it. And phi times u means stretch the vector phi times. And minus 3v means in opposite directions, 3 times as long. And I want the combinations of these, add these two together, 5v plus minus 3v. So I draw the parallelogram or use the base to tip rule. And that vector formed is the vector phi u minus 3v. The vector phi u minus 3v obtained in this fashion from u and v, it's called a linear combinations of u and v. This term is very important. Linear combination of some vectors, meaning you use those vectors, you add them, subtract them, and make a new vector. The new vector is called a linear combination of the old one. Here's a length. Okay. And then we have the notations that so-called the IJ notations. If I don't want to deal with this little bracket with a comma, 1 zeros, I can use these I and J notations. Then I can write the vectors AB as AI BJ. So 3, 2 is 3i plus 2j. Then I can track all these additions, subtractions, operations like algebra, like x and y, except I and j. And so I can track subtraction using IJs, and it's a convenient way of doing it. And all these things we went through apply for the three-dimensional space. So I'll let you read that, and that's it. This is the sections basically on vectors. And see you later. Bye-bye.